Welcome back to Physical Geology. This next section is going to deal with this trout run little topographic map document here. We'll see that we're going to complete these items A through H on here. Then we're going to come back and answer this question here. But let's look at this map, and I'm going to show you how I'm going to draw it here on the document camera. So for starters, it's asking us about the contour interval. And remember, to figure out the contour interval, we need to count the elevation difference between each contour line. So for example, if we're going from 100 here up to 200, count the number of steps you take and then divide 100 feet by that number of steps. And that'll give you the contour interval. Then you can estimate, or at least in this case, you can get exactly the elevation of point X, right? So this index contour is 200 feet, so it's going to be 2 contours above that. So you'll put that number there. And then elevation B is easy. That's sitting right on 100 feet. Elevation A, again, you got to figure out your contour interval to figure out what A is. And then the distance between A and B, well, if you see the bar graph here, it's about 1 mile. They make it pretty easy here. That's 1 mile. And then to figure out the gradient, it's going to be the elevation difference, the rise over the run, right? So whatever elevation it is between A and B divided by 1 mile. And that'll be your gradient. And then you're going to want to shade in some areas here. You're going to also want to draw the drainage divide here. So that's what we need the document camera for. So we're going to shade in some of these high points here. So I'll do some of them here. So once you shade in those high points, you're going to be asked to draw the drainage divide. And that's where we're going to make an outline, kind of a dashed line, will show the divide, or at least, so for example, if water were to land here, it's going to flow away in this direction. But if it lands here, it's going to flow into the Trout Run Basin, right? So that's what we're doing this divide here. So again, if any water is landing here, it's going away. Here, it's going into our basin. And so we'll complete this, and it's going to wrap around here and end up going down the hill there, right? So again, water here is going away. Water here is going into our basin. Now, coming around this way, it looks like if any water lands here, it's going to go off in this direction here. So our divide has to come right through here and then right through here. So any water landing here is going to end up going down this way. So again, we're going to be right on this ridge top here. And again, here it's a little tricky where water landing, so see this V, that means there's a stream going off in that direction. So that must mean that this divide must be right in here somewhere, something like that. So where water lands here, now the V's are going this way, so it's going to go down in that direction. And then we're going to make our way down this way and then off the page. So that would outline our drainage divide. So that's what they want you to do there. And then use the rule of V to figure out which way Trout Run is flowing. And then don't forget to go back and answer this question on this oil drum, right? So that's it for this one. It's pretty straightforward, but it's a good little kind of review of streams and going back and look at our topographic maps. Now the next few problems deal with some maps that are included in the lab. And again, you don't have to print these pages. You can just look at them on your computer. And this first one is the Lake Scott quadrangle, and it talks about how the geology, most of the beds, or the strata is tilted toward the east here, and most rivers are draining eastward here, right? And so Lake Scott is a region right in here of western Kansas, so kind of in this region right here. I think the stream we're looking at is one of these right in here. We'll be looking at this Timber Canyon, and we're going to be measuring gradient and sinuosity between point A and B and C and D. And note that for the Timber Canyon, the blue, you can see there's a good meander, a good kind of curve or sinuous there, right? So this one has a little bit more sinuosity, then it's going to curve way through here. But the Garvin Canyon is pretty straight river, right? So again, when we're looking at the numbers here, we're going to be looking at that Lake Scott quadrangle map on page 8 here, and we're going to measure the gradient of this upland surface. So here's the upland surface, that old tilted surface that tilts from the Rocky Mountains over here all the way toward eastern Kansas, right? So we want to measure that gradient. So what I want you to do is measure this with a ruler, and there should be a scale here, right? That gives you miles. Yeah, so use this for miles over here for your scale. That'll give you the distance. And then the elevation drop, you have to figure out the contour. So remember, the contour interval here is 10 feet. So if that's 3,000, then this contour line is 3,010. So the elevation of point B must be 3,010. And over here they tell you elevation A is 3080. So it's dropping 70 feet over the course of that distance. So you can do that, do the math right here. Now, what is the name of the modern stream drainage pattern, right? So is this looks like it's dendritic, and that's very typical of this. In fact, this whole area, you can see that's dendritic pattern, kind of this veiny pattern. So, and then now you want to figure out the gradients between A and B and C and D, as I was mentioning earlier. So again, the contour interval is 10 feet. So if that's 30-50, 30-40, 30-30, 30-20, 30-10. So A must be at 30-10, whereas B is right on this index contour right here, which is 2,900. So it's going from 3,010 feet to 2,900. So that's 110 feet. So it's dropping 110 feet. So again, you can do the math. That'd be the gradient. Now just take your string, right? In this case, your string's going to be pretty straight, and you can see it's going to be a little bit less than a mile there. So you can get the gradient for A and B. And make sure you record those numbers here for gradient. And then you'll do the sinuosity. Again, you'll take that curvy path like I showed you, and then the straight path. And then when you record those numbers on questions 3 and 4, make sure to come down over here to this page here, and you want to add those numbers here for Garvin Canyon and Timber Canyon, and also add the Missouri, Arkansas, Mississippi River data you took earlier, because we're going to plot this on this. So here they're asking us to draw the drainage basin for Garvin Canyon. So it's a close-up of this map here. We're just looking at Garvin Canyon. They've already done Bettendorf Canyon here. You can see they've in red they've outlined the divide or the watershed for Bettendorf. So our job is to do it for Garvin Canyon. So let's do it on the document camera here. Imagine water, you want to look at these rules of V. So I see the V's here pointing up, so that means water is going off in that direction. So that must mean any water here is going that way. Here's the V, water's going that way, water's going back this way. But since I see V's here, water's going to be going into Garvin Canyon this way. So our divide, and then here's a V pointing uphill, so maybe right here. So our divide is probably going to kind of come off the Bettendorf divide here and go around like this, right? So any water landing here goes into Garvin Canyon, here goes off into this other canyon to the north there. And then again, you want to show this divide coming through here. So again, I've seen all these are going into Garvin Canyon, so I'm going to have to include all this in here. But now anything here will go off in this direction here. So I need to be, in fact, no, I can't include that because everything here is going to be going that way. So I got to actually come down this way. Yeah, here it is right here. And then I drop down to, so that closes off here. But then here, there's a separate canyon here. So I have to come off in this direction here. So that would be my drainage basin for Garvin Canyon. For the next map, this Strasburg, Virginia map, which is on page 10, this map down here, we're going to be doing the same thing. We want to figure out what type of drainage pattern that this one is. So now here we have a main stream, but then we have many little streams that are coming in at right angles. And then what does that type of drainage pattern tell you about the geology, the bedrock geology? So you can answer those questions. And then on this one, they're also asking us to figure out the gradient for the stream from E to F. So that's this little stream up here, E to F. So it's a pretty straight stream. And also for Passage Creek from G to I here, G to I. And so again, you'll use a string here. You'll use the scale there. Yeah, here's the scale here in miles. And here the contour interval is 20 feet. So work on that one and get the gradients and the sinuosities for both of those streams. The next problem here is dealing with this Ennis Montana map. And Ennis Montana map is this map right here. And kind of this is a larger 15-minute series map here. And we have a big alluvial fan here, right? You can see the contours showing this big alluvial fan. And the stream here is coming through here. It's pretty high gradient here. Then it enters this alluvial fan. We're going to answer some questions on this Ennis Montana map. What main stream channels are present? So for starters, in the forested area up here. So over here, they're pretty straight. So really what I'm looking for here are answers like, are they braided, are they sinuous, or are they meandering, or are they straight? So pick one of these here. So now what we're going to do, this is an enlarged portion of this Ennis Montana map. So we're taking this section here and we're enlarging it here. And our job is to make a longitudinal profile from K through J. So basically wherever there's a red dot, we want to record that elevation. They've already done this letter K for us at like 7,400, right? So it looks like for here, they have each of these is 100 feet, right? So on the vertical scale. So let's look at I actually printed this one out, so we'll do it over here in the document camera. So I'll start here with, they've done this point down here at 5,800 feet. And then we go, this is 6,000 feet. So 6,000 feet, you come straight down to where 6,000 is. 6,000 is right about here. And so we'll put a dot right there. Then we'll go over, and this is the next one up, which is at 6,200. So 6,200 for where letter L is. And so that's 6,100, 200 right there. Put a dot there. And then this must be at 6,400. So 6,400 would be right on this line here. Put a dot right there. And then here we have 6,600. So 6,600 would be right about there. You can see I'm just following this up here. And this is 6,800, which is right around in here. And then 7,000, which is this one right here. 7,000 will go right in there. Then I have the 7,200, which is that point right there, which is going to plot right around in there. So then I can connect these points to show the longitudinal profile. So it's higher gradient over here, and it starts to flatten out over here. Now we can answer some questions regarding this. So we completed that profile here. The questions they're asking us are here. So observe this profile that we just constructed. Label the profile bedrock eroded and then sediment deposited. So on that one, because it's steeper here, and also on the map it's showing that there's more forested region here, so we're closer to the bedrock. So anything really from L above, this would probably be bedrock eroded up here. And then now you can answer these questions regarding that profile for question number 4. Now you have all your data and you can plot it on this graph. And then I want you to see if there's any relationship based on really on how steep or the gradient is, and then whether it's sinuous or linear. See if there's some relationship. And you want to answer this question 3.